First of all, let's talk about the problem statement. The simple conventional ripple carry adder RCA that composed of multiple cascaded single bit full adders has lower computation speed because the next full adder has to wait for the carry out signal from the previous full adder to carry out its operation afterwards. Therefore, carry select adder CSLA is used to replace RCA in order to reduce the carry propagation delay of multi-bit adders at block level. Nevertheless, the conventional regular CSLA is still not area efficient enough due to the usage of dual pair of RCAs to produce sum and carry, where the final sum and carry will be selected by the multiplexer. As a result, square root CSLA, which is an extension of linear CSLA, is developed for equalizing the delay and area of two carry chains and the block multiplexer signal from the previous stage. Square root CSLA has a more balanced delay, requires lower power, and more area efficient. There are some other methods that can be used in modifying the regular square root carry select adder. Firstly, is by using Brand-Cone adders. Brand-Cone adder is a parallel prefix adder form of carry look-ahead adder. In parallel adder architecture, the critical path for the carry to reach the most significant bit adder can be reduced, because the critical path is determined by the computation of the carry from least significant bit adder to the most significant bit adder. It is used to replace the upper RCA for faster operation. Although the Brand-Cone adder is simpler in architecture, but it has higher fan-out, which leads to lower speed of adders due to the weaken of signal propagation. Next is zero finding logic. It is designed by means of half adder in cascaded form. The output from the XOR gate is the final output, while the carry from the half adder is provided as the input for the next stage. As a result, the carry will be the output of the final XOR gate. The utilization of zero finding logic as the second stage of the CSLA is to remove the RCA with Cin equals to 1 and the final multiplexer stage in the conventional CSLA. Nevertheless, the propagation delay of the circuit will increase. So now our solution, and why is it better? Binary to access 1 converter is a digital circuit that accesses input value to 1, which means the value of input is increased by 1 with the aid of BC. BC is composed of 1 NOT gate, 2 AND gates, and 3 XOR gates to perform its operation. Binary to access 1 converter is used to replace RCA with Cin equals to 1 in the regular square root CSLA. In practical, the BEC circuit consists of lesser number of logic gates than the n-bit full adder structure. The binary to access 1 conversion method is chosen as the best approach to fulfill the design requirements of this project. However, there's a limitation of this BEC method, which is it may cause a slight increase in the propagation delay in the modified square root CSLA structure. As for the other methods such as using Brand-Cone adders and zero finding logic, the reduction of power and area are not that significant as compared to BEC approach. The development of high-speed adders is very important in the most commonly used arithmetic operation on digital signal processing applications. For applications like RISC processor design, usage of an efficient adder in the circuit is critical because single-cycle execution of instructions is the key measure in circuit performance. Hence, for practical applications, the adder should feature high speed, area efficient, and low power consumption. The cost of VLSI system can be reduced by improving an adder's performance, such as carry select adder designed in this project, in terms of area, power, and delay using more advanced technology.